When Mach breaks, you have the wish to go on top and then jump. But when your Mach doesn't perform.
Well, I asked you.
This is like the iron dome.
Oh, yes, yes.
That's
I see.
the operating system is called the sun.
Ah, yes, yes.
Named after the Yosemite Sam.
All right.
Yeah, we start 5 minutes later.
Okay. No problem. So thanks for the introduction. Also thanks for the organization.
Okay.
It's a great pleasure to be here and be able to present my research. So I will talk about two things today. The first one being how one can describe the dynamics, closed exceptional points. And in the second part, I will talk how one can use the peculiar phenomena we encounter when we are close to these singularities for actual applications. And to give you at first some introduction. Yes, sure. Is it better now?
Tap on it.
Yes. Hi. Okay. I'm afraid I've swallowed. Okay. Better? All right. Okay. Okay. So first, what is an exceptional point? To take this my artistic approach at drawing two coupled oscillators. So with respective relative frequencies omega and minus omega, and loss rates gamma and minus gamma. And both oscillators are coupled with a coupling G. And the system can be described with the Schrödinger equation, so for equation of motion for the amplitudes beta 1 and beta 2. The Hamiltonian here is given by this two-level system here, which is a non-Hermitian system, as you might know. And for these quantities, we can have the situation depending on the parameters omega, G, and gamma, where not only the eigenvalues coalesce, but also the eigenvectors. And this is what we call an exceptional point. And this is in contrast to Hermitian physics, where we can only achieve that the eigenvalues are degenerate while the eigenvectors remain different. Now, for this problem, you can easily write down the eigenvalues. You have here the square root behavior. And these are now general complex quantities. We can now draw the spectrum as a function here of omega and G of the coupling and keep the loss rate fixed, for example. And we have here now a real part to the left and an imaginary part. And you see this peculiar structure of intersecting Riemann sheets. You can see here, and exactly at this pinch point here is the exceptional point. Now it will be relevant in the following. So here the coloring corresponds to red corresponds to gain, and blue corresponds to an eigenstate with loss. Okay, and when you look at the structure, and it's a very natural question to ask based on Hermitian reasoning and Hermitian, when you think of the adiabatic theorem, if you now place a state here on the red upper sheet and go in a closed loop around the exceptional point, and you will expect, so this is schematically shown here, and you will expect that you make an adiabatic flip, as we call it, from one state into the other, even though you arrive at the same parameters in which you started. So the parameters here are the coupling and the relative frequency, which would be a very nice thing to have. Now, before we can now think of if this really works, at first we have to ask the question if this Riemann sheet structure is a physical reality. And this question has been asked almost 15 years ago by Nembowski and co-workers, where they carried out a microwave experiment, which you can see here schematically. So you have two coupled microwave cavities coupled with an opening slit of size S. This is the first parameter. And the second parameter would be the deflection of the center of the circle of a definite semicircle. This gives rise to a second parameter delta. And in this system, now the real part of the eigenvalue corresponds to the resonance frequencies, and the imaginary part corresponds to the resonance widths. And what it did now was to fix a certain parameter S and delta, and then record the eigensystems, so the eigenvalues and the field distributions, and then they changed them and did the same, and with this they described a loop around dp. And here you can see indeed the instantaneous eigenvectors, so the eigenvectors for a fixed parameters S and delta make a flip. And this was a very important experiment and gave a lot of insight, but unfortunately it didn't study the full system, actually the full problem of dynamically changing the parameters. So where S and delta here would have a time dependence. And this was done by Ustin, Malebaev, and Moseyev in 2011 in this paper here, where they at first expanded their state in the instantaneous eigenbasis V plus and minus with coefficients C plus and minus, and this then gives rise to the Schrödinger equation in the eigenframe. And you see here you have in a diagonal the eigenvalues, and you off diagonal the function f, which is the non-adiabatic coupling. And normally when you are in Hermitian physics, you want this is the adiabatic condition, so that the non-adiabatic coupling is much, much smaller than the distance between eigenvalues. But if they now, for this system, studied it and looked at the full problem in their own words, what they found is undecided states get populated and the perfect flip effect expected from the instantaneous eigenstate basis is ruined. And so in general, the adiabatic theorem is not valid in non-Hermitian systems. And therefore we will call this not the adiabatic condition, but the quasi-adiabatic condition, as we'll explain in the course of my talk. So now let's look at specific examples. So we're solving this equation now numerically. And what you see here is again the Riemann structure, the real and imaginary part. And what is this trajectory is now a numerical solution and projected onto the respective Riemann sheet to give you an indication of the quality of the solution. So in this case here, we start here, our evolution, and we spiral after a loop to the upper state. So this would correspond to our adiabatic expectation, basically. However, if we don't go in an anti-clockwise direction, but from the same state in a clockwise direction, we see that we actually end up in the same state in which we started. So here we have a non-adiabatic transition close to the starting point of evolution. And the third example I want to show you, here now the Riemann sheets are rotated by 180 degrees. Overall, the dynamics look adiabatic, since you start here and make a flip. But in the interim of your evolution, it's highly non-adiabatic. So you have here one non-adiabatic transition right at the start, and right almost at the end, a second one. And this is what we want to explain, also on a very intuitive basis. And for this, we are not solving actually this equation for the amplitude C plus and C minus, but actually we are building the ratio of those two, which gives rise to this Riccati type equation. And this R is now called the non-adiabatic transition amplitude. So to give you an idea what this tells us, so if we initialize our state in the C minus eigenstate, C plus at t equals 0 is 0, and if we were adiabatic, we would follow the minus eigenstate the whole time, and R would remain 0. This would be the adiabatic expectation for this dynamical parameter. However, if there are non-adiabatic transitions, we will expect that this assumes a finite value. Okay, and we'll solve this equation, this nonlinear equation R, in the quasi-adiabatic limit, where f is much smaller the distance between eigenvalues.
May I make sure? That point in the omega g plane
Yes.
is the exception point.
It's here.
That one?
This here, yeah.
But,
But we're never going through it, we are encircling it.
Right.
Yeah.
But the relation include the I gamma over 2, right?
Yeah, one parameter is fixed. We fix, in this case, we fix the loss. And we vary the relative frequency omega and the coupling g.
I'm wondering why it is on the omega g plane. Because
Well, your spectrum depends on these parameters, right? In our case,
well, I
we
mean,
fix
omega equals g plus I gamma 2 or something. Yeah, right? So how does it?
I go back to the where I have it. So here is the eigenvalue, yeah?
Oh, so
And we are free to fix here gamma, and just vary omega and g. And this is what you see here, the spectrum depending on these two parameters. Okay?
Omega is 0. Okay.
All right.
You can set omega to 1 because you don't need a ratio. That's the scale.
No, I just wondered why that EP exists on the real omega and real g plane. Okay.
Okay? All right. Okay, let's go back. Yes. Okay, so we're now studying, rather than this differential equation, we're studying this here, this Riccati equation. And we will now look at how R behaves as a function of the time for this specific example here, because this is the most non-trivial case. And this looks something like this. And I want to emphasize, here we don't just look at one loop around the p, but actually we look at the periodic problem. Here you see the time scale is 4 times the period.
Could you remind us how you picked F? What is the form of F?
F is, if you go into the eigenframe, these are the non-adiabatic couplings. Okay. And if you now look at the solution here, you see the square wave behavior, and you have extended prolonged episodes of quasi-stationarity here and here. And this becomes clear when you go back and look at this equation here, and you notice the following. So this is a singularly perturbed problem by the non-adiabatic coupling, which means that you cannot obtain the solution for this as a small correction to the solution of the adiabatic limit where you have no non-adiabatic coupling. And this is also the reason why we call this the quasi-adiabatic condition, so F much smaller than 2 lambda, because this alone does not ensure adiabatic dynamics. What's also in this is a representation of a slow-fast problem, which evolves on 2 time scales. So for very short times, lambda and F are almost constant, and then the system converges rapidly to 2 fixed points in the system. And the fixed points are given by 1, which is given exactly by the non-adiabatic, by the quasi-adiabatic condition, which is much more small than 1, and this we can identify with the adiabatic solution, with the adiabatic fixed point, which we call it, which is exactly here on this level. And the other fixed point, which is possible in the system, is a non-adiabatic fixed point, which is this high value here.
This equation has a symmetry. If I divide both sides by R squared,
Mm-hmm.
I see that R and 1 over R satisfy the same equation. So
Yes, yes.
so
This is a simplification, yeah. It's true, yeah. It's true. 1 over R would then correspond, yeah, just for the other, if you initialize the other state. You're right. And we can now ask about the stability of these fixed points. Okay? Okay, and we can ask about which conditions are these stable, and this is stable if the imaginary part of the eigenvalue is smaller than 0, then this one is unstable, and if the sign of the imaginary part of the eigenvalue is switched, also the stability of these 2 switches. So then this becomes repelling and this attracting, and this you can see here in this cartoon here. So this would correspond to the situation here, where we would spiral fastly towards the adiabatic fixed point when this is an unstable one. For on long time scales, the stability can change. So we expect that there are dynamic bifurcations in the system. So consider here now T star corresponds to the time where the stability swaps of the fixed points. So here we are attracted by the adiabatic fixed point exactly at the point where the stability changes. Both fixed points are centers and not attracting or repelling. And for times larger than the critical time T star, the adiabatic fixed point becomes repelling and the non-adiabatic fixed point becomes attracting. And what's now strange is, or unexpected, so these times where the stability changes is here denoted by T star. And you see that even though here the stability changes, there is not an immediate transition from one fixed point to the other, but there is a delay, which we call here the t plus. So the basically loss of stability when you encircle one or approach one fixed point is delayed. And as it turns out, this is a very common phenomenon in the slow, fast systems with dynamical bifurcations, and is known as the stability loss delay. And this was found by Neistat in the late 80s. So basically, to describe the system dynamics, you need two quantities. The first one being when does the imaginary part of the eigenvalue change sign? It's easy, you have this because you parameterize your Hamiltonian and also have the eigenvalues. And the second quantity which you need to know is this quantity t plus, so the stability loss delay time. Now I want to mention for completeness that there's a very close connection to Stokes' phenomenon of asymptotics, which denotes a switching on of a small exponential in the asymptotic expansion of your solution. However, this unfortunately just tells you that something will happen, but it doesn't tell you when it will happen. And this is exactly what the stability loss delay gives you. And finally, we have also investigated how noise changes our solution of this system. So here in gray, you see 10,000 stochastic integrations of this non-adiabatic transition amplitude R. And you see at first, stability is lost earlier because we are quite sensitive to initial conditions. But already after the first period, you see that we are very robust with respect to noise in the system.
What determines the slope of the line?
This slope here? So in our description, we basically model this by just a discontinuous jump. But if you look real closely to it, like those two guys, so Barry and Ustin did, you see it's an error function. Okay. All right. And we can now revisit the first example I've shown you. So, and don't be confused. So here, actually, what we plot is not the imaginary part, but actually it has a minus sign. So here, the adiabatic fixed point is not stable for a negative part, but for a positive part. Here we follow the adiabatic fixed point the whole time, because the stability, so the imaginary part, never changes sign. Okay, so we always follow. That's why on overall, the dynamics are adiabatic. In the other case, you see here, the adiabatic prediction would be that I follow the blue sheet here, so the imaginary part is always negative. So we are always, always the adiabatic fixed point is unstable, and we initialize close to the adiabatic fixed point, and because of that we transition away from it and make a flip, a non-adiabatic transition to the non-adiabatic fixed point. That's why in overall, the dynamics are non-adiabatic. And in the third example, you see that we have the same situation, so we initialize to a state which is close to the unstable adiabatic fixed point. We make a transition after some time, but then in the interim of the evolution, the stability changes. And then after a stability loss delay, we switch back to tracking the adiabatic fixed point. That's why in overall, the dynamics appear adiabatic. All right. And now, so second part of my talk, we want to ask the question how we can use the non-applicability of the adiabatic theorem for actually an real-world device. So again, I show here this projected on a Riemann sheet on the real part this time. And think now of a state here on a blue sheet. You go in a clockwise direction, and it ends up in the same state in which you started. If you go the other direction, you actually switch to the upper sheet. If you initialize to this upper sheet here and then go in a clockwise direction, you switch the sheets, and if you go the other direction, you stay in this state. And now consider in a linear system, a linear combination of those two, and you go in a clockwise direction, yields basically that you are you result in basically the first state, which you call here the blue sheet, and the red sheet would be the state 2, with a very small impurity of the second state. And if I take the same linear combination and go the other way around the exceptional point, we obtain that we are majorly in the second state. So, and we want now to use this fact for such a waveguide device here. So here I inject from the left two modes. Here in red the first mode, in green the second mode. Then something magic happens. And at the end of the system, for the most part, the state is composed of second mode. And if I do the same from the right side, mostly the first mode comes out on the left side. And this would correspond then to a device which, depending on the input direction, yields a specific output signal, and which would be the first very nice thing to have, because you're basically using a nice property of exceptional points, but also for applications. Think of optoelectronics, for example. And the question now is how one can use or perturb this waveguide system to induce this transition. And it turns out a very efficient way to do this is via a boundary modulation, which you can see here, where the amplitude corresponds to coupling between the propagating modes, and the frequency imprinted in this boundary corresponds then to the detuning. And this system can be mapped to this Hamiltonian here, very similar to the one I've shown you before, which is non-emission, obviously. K1 corresponds to the wave number of the first mode in x direction. Gamma 1, gamma 2 are the loss rates of the modes, G is the coupling, and delta is the tuning. And we now want to encircle the exceptional point by using parameterization of G and delta here to describe a loop, a closed loop, in the presence of loss. And if you do this numerically, you obtain this situation here. But let me guide you through it. So at first we have constant loss, and what you see here is the wave function intensity on a logarithmic scale. Okay, and what you also have is that this system is not to scale, so the length is 100 times the width. So I have to compress it, otherwise I wouldn't be able to fit it onto my slides. And if I inject the first mode here, you see it makes a switch to the second mode at the end of the waveguide. While I inject from the left the second mode, it is almost completely damped at the end of the evolution. However, if I inject the first mode from the right side, so it doesn't get as far, it's more strongly damped than the second mode, which switches to the first mode. So this is already well, a realization of the concept we had. But however, since this is on log scale, it's not very convenient, since the overall intensity at the end of the waveguide is on the order of 10 to the power of -7. So it's not very sexy. But we didn't stop here and thought, how can we make this better? So you need a strong asymmetry between both modes. So you either need a very large system or you need large loss. And both doesn't work in our favor, since both attenuates the wave. But you can actually look at the limiting case of not both modes feeling the loss, but actually one mode being basically unperturbed, while the other mode is maximally damped. And this you cannot achieve with a constant loss, but with a position-dependent loss, which you can see here. So in the blue dots which you see here corresponds to a Gaussian-shaped loss potential. This is due to an optimizing procedure. And if you repeat your calculations with this loss switched on, we obtain this, which is now much, much nicer. So here you see this was the mode chosen to be basically unperturbed, while this is strongly damped, and the ratio of the populations here is on the order of 10 to the power of 4. And if you go in from the right side, you see that the first mode is almost completely damped already at the entrance of the system, while the second mode propagates unperturbed. Okay. So this is nice. However, the system is very bulky. It's still 100 times the width. So we went again one step back and thought how we can optimize this. And there are several techniques which allow it to do this. And also you need some intuition. And what we then obtained, which we're very proud of, is actually we could reduce the system size by 1 order of magnitude. So this is here now 2 scale. So the length is now 10 times the width. As you can see here, which achieves the same. So think here, if you inject both modes, you obtain basically just the second mode on the right side. If you go in from the right side, you obtain the first mode here. And this is really nice to see, since you only basically here see a few wiggles are sufficient to achieve this. All right. So with this, I want to come to my conclusion. So in the first part of my talk, I presented you a general description of quasi-adiabatic phenomena when encircling exceptional points. We find that the dynamics are controlled by fixed points, which exchange stability, so this due to dynamic bifurcations, and the solutions don't switch immediately, but actually only after a stability loss delay time. And we also find, which is a property very important for experimental realization, that we are very robust to noise as well. In the second part, I've shown you a robust asymmetric two-mode switch, which uses exceptional points, for which you also could greatly reduce the device dimensions while retaining the device quality. And we can now actually think of an experimental realization of this scheme. A very quick way to do this would, for example, be a microwave setup, which you can see here, but where our device would actually literally really shine would be on the micro and nano scale, for example, where you can see here a silicon waveguide with germanium and chromium constrictions. Before coming to an end, I want to thank the people involved in this. So the first part of my talk, the most part of the work was done by Thomas Milburn from the group of Peter Rabel at the Institute of Atomic and Subatomic Physics in Vienna. Then there's Stefano Portolan from the University of Southampton and Catherine Holmes from the University of Queensland, and finally Stefan Rotter, who is my PhD advisor from the Vienna University of Technology. And for the second part of my talk, those three gentlemen also contributed. Additionally, we have Alexei Malebaev from the Institute for Pure and Applied Mathematics in Rio de Janeiro in Brazil, and Adrian Gierschik and Florian Liebisch, also from the Vienna University of Technology. And if you're interested, you can find the archive preprint of the first part under this link here. And the second part of my talk will find its way on the archive, hopefully in next weeks. Thank you.
Thank you so much. So, question?
If you circulate not near the exceptional point, rather make a bigger loop, will that make it more stable or switch in more time?
You would have higher non-adiabatic contributions. So actually you need to be kind of far away enough from the degeneracy. Okay? If you're too close, you would need longer times, basically. If your loop is too close to the exceptional point, you would need larger times or larger system lengths to see these effects which we're using. Yes.
Only have these two modes, or is it possible that there are further resonances with additionally non-adiabatic couplings, which
So,
a complete loss of the intensity out of the system?
I mean, this is a proof of concept. You can extend this, I'm very, very sure, to more modes. But since it's the first starting point, we just looked at the problem of two propagating modes. But I think there's no problem, really, to extend this. Yeah.
Additional questions? Yes, Adi?
Clarification, just didn't get it. Why did ending the waveguide shorten the distance? Why could you do better with a curved waveguide, and how much better can you do it?
In relation to what, exactly?
I think the goal was to reduce the length over which you...
Yeah, sure, yes. Mm.
So why I
Look.
would think that if you bend it, you'll have more scattering, that it would work
Yeah.
better.
This is what you expect, but actually it turns out, I mean, you have to parameterize your parameters, right? You switch somehow with some function, the roughness on and off, and you have some the tuning, which also depends on the function. And there are some very, very nice schemes out there which ensure that you do it fast.
To optimize.
Yes,
the-
yes. It's heavily optimized, yes. Yes.
Any other questions? If not, it's time to thank our speaker again. Okay. Just a second before you